Good evening to every one of you, my dear students. Yeah, last class we discussed in chemical bonding the last topic, that is bond parameters. We are doing one parameter that is called bond length. We completed. Now let us start today. Next, bond energy or bond enthalpy. Bond enthalpy or bond energy. What is bond energy? For example, beryllium chloride. Between beryllium and 2-chlorine, 2 covalent bonds are formed. Right. You want to break these covalent bonds. For what purpose? To participate this molecule in chemical reaction to combine with other molecule. For that purpose, you have to break the covalent bond. How many? One covalent bond? No. In chemistry, the total chemistry we are considered 1 mole is considered as a unit. To break 1 mole of covalent bonds, no doubt you have to supply some amount of energy. The amount of energy which is required, which is needed to break 1 mole of covalent bond is called bond energy. The energy which is required to break 1 mole of covalent bonds is called bond energy or bond enthalpy. To break 1 mole of covalent bonds, right? Then different covalent molecules are existed. To break all these covalent bonds that are present in the different covalent molecules, same energy required? No. The energy that is required to break the different covalent bonds of different molecules is different. Then how can you predict it? That is, the bond energy of different covalent molecules is determined by using some factors. You have to know it by using some factors. You have to understand it by using some factors. Now let us start to discuss about factors influencing the bond energy. Factors influencing bond energy. Factors influencing bond energy. One by one. First one, bond energy is directly proportional to number of covalent bonds. Number of covalent bonds. Bond energy is directly proportional to number of covalent bonds between two atoms. Between two atoms in a molecule. Right. For example, here carbon single bond, carbon double bond, carbon triple bond. You take it, this is a C2H6 alkane, C2H4 alkene, C2H2 alkyne. This is ethane, ethene, ethyne. So in ethane, between two carbons, single bond is present. Here, ethene or alkene, between two carbons, double bond is present. And in ethyne, alkynes, triple bond is present. No doubt, to break the 3 covalent bonds, you need to supply more amount of energy. That's why bond energy of alkynes is more, because number of bonds are more, and the alkenes is less. That is, and alkenes is more than alkane. Why? Because the number of covalent bonds in case of alkene between the 2 carbons is 1, between the 2 carbons is 2, between the 2 carbons is 3. As number of covalent bonds increases, then what happens? Bond energy also increases, because number of bonds increases. You have to supply more amount of energy to break all the covalent bonds. Then only it can participate to combine with another molecule to produce a new There is a product negative reaction. Next one. Another example. Take a carbon oxygen single bond, carbon oxygen double bond, carbon oxygen triple bond. If you observe here, this is CO2 minus, this is case of CO2 molecule, this is case of carbon monoxide molecule. So what is the order of or increasing order of bond energy of these molecules? Right. So here, if the carbon oxide single bond is there, here double bond is there, and here triple bond is there. So that's why carbon monoxide is bond energy is very high. Next carbon dioxide, next carbon dioxide. Next, take it here carbon nitrogen single bond, carbon nitrogen double bond, and carbon nitrogen triple bond. This is we observe here. For example, CH3 NH2. There is a methyl group, and this is amine. This is methyl amine or aminomethane. Aminomethane or methylamine. One carbon is the with plus N plus amine, methylamine. And this one, already two bonds are there. Remaining two bonds with two hydrogens, CH2 double bond, NH2. Right. CH double bond, NH. Already two bonds are there. So nitrogen have three bonds. So here two bonds, and with one hydrogen have one bond. So 2 plus 1, 3 bonds. Right. These are called amines. And here this is a cyanide group. So cyanides. So which one having highest bond energy is no doubt cyanides have more bond energy. Next amines, next amines. Right? Got it? Cover it first. Next one. Another factor, second factor, bond energy is directly proportional to percentage of s orbital character. Percentage of s orbital character. How, for example, if you take sp hybridization, sp2, sp3. Here, percentage of s orbital character is 50%, and this one, because here 1:1%, and this is 33.3%, and this is 25%, right? So, for example, they give beryllium chloride and boron trichloride and carbon tetrachloride. So, which one having highest bond energy? Means here you can consider here s orbital character is more. Here beryllium undergoes sp hybridization. S orbital character is more means electronegativity more. That's why bond attraction is more. That's why you have to supply more energy to break the bond, because the two bonds with the beryllium and chlorine, the bond attraction is more because the percentage of s orbital character is more. That's why overlapping is strong. Overlapping is take place. That's why stronger covalent bond is formed. To break that, you have to supply more energy. Right? Next one. Another factor, bond energy is directly proportional to number of lone pairs of electrons. It is directly proportional to number of lone pairs of electrons. Right. For example, take it CH4, NH3, and H2O. Right. So here, what happened? CH4 with the carbon and 4 hydrogen, all four valence electrons are participating in bond formation. No lone pair. There no lone pair. So number of lone pairs is 0. Here on nitrogen one lone pair is present because it utilizes, so nitrogen have 5 valence electrons. Among the 5, it can utilizes 3 valence electrons to form 3 covalent bonds with 3 hydrogens, and still 2 electrons which are not involved in bond formation. They are lone pairs or non-bundle electron pairs. There is 2 electrons, 1 pair. So 1 pair, 1 lone pair is present over nitrogen. In the same way, oxygen having 2 lone pairs. Here 0 lone pair, here 1 lone pair, here 2 lone pairs. As number of lone pairs increases, repulsions between them increases. That's why repulsions are more, these attractions are less. The bond is less tightly holded. It's very easy to break the bond. That's why it is less bond energy. There are no lone pairs. All our bonds are there. Bond pairs are more. So strong bonds are there. Number of bonds are more. All our bonds are. So the attractions are more because lone pairs are not there. Lone pairs are there. Repulsions are there. Lone pairs are not there. Attractions are there. That means, what is attraction means here the electron valence electrons which are participating in bond formation, because they get attracted, then the strong bond is formed. That's why it is more. So that's why the bond energy is inversely proportional to number of lone pairs. No lone pairs, bond energy more. More lone pairs, bond energy is less. Next. Next factor, bond energy is inversely proportional to directly proportional to electronegativity of central atom. Directly proportional to electronegativity of central atom. So electronegativity of which one? Central atom. Central atom. For example, take HF, HCl, HB or HI, right? So which one having highest bond energy? Fluorine electronegativity is more. Iodine electronegativity is less, right? And that too, hydrogen and fluorine. Fluorine is smaller size. Fluorine is smaller size. And iodine is larger size. Hydrogen is common, but it is larger since bond distance increases, bond length increases. That means the two atoms are away from one another, so attractions are less. Attractions are less means it's very easy to break the bond. That's why there is their electronegativity is less, bond atomic size is more. Atomic size is more, electronegativity is less. That's why it is very easy to break the bond. So I minus is readily formed. It is very easy to break the bond. But here with the hydrogen fluoride, strong attractions are there because size is smaller, and the electronegativity is very high. So attraction forces are more because of that. So electronegativity is strongly attracted, thinly pulled across. It's very difficult to break the bond. So that's why bond energy is more. That is directly proportional to electronegativity of the central atom. Next, one more example. We take here. So NH3, so PH3. ASH3, S3H3. So all belongs to 15th group hydrates. 15th group hydrates. So here electronegativity of nitrogen is very high, then its proportional decreases. So that's why it is very high NH3 and SPH3 is very less. Next, one more here. So take here NCl3, 3Cl3, ACl3, SPCl3. So here, if you do it from nitrogen to there is antimony, whatever electronegativity decreases, so that's why bond energy is also decreases. Next, one more example here. So H2O and the H2S and the H2Se and the H2Cu take it here. So what happened here? Electronegativity of oxygen and hydrogen, that is oxygen is more and helium is very less. So that's why it is very high. That too, H2O, it forms hydrogen bonds. Hydrogen bonds are there. That's why the two H2O molecules are held together through hydrogen bonds. So that's why they form associated molecules. One water molecule linked with another water molecule through hydrogen bond. It is linked with another water molecule through hydrogen bond. And then it is linked with the other. It is linked with, like that. So many water molecules are linked through hydrogen bonds and forms associated molecules. The molecules are that associated things now supply more energy to break the bond. That's why it is a high bond energy is required. Right? Got it? Copy it, all of you, my dear students. This is the concepts you have to prepare regarding bond energy. Next one, another bond parameter, bond angle. Bond angle, right? What is bond angle? For example, if you take it beryllium chloride. So beryllium, the central beryllium chloride, the central atom beryllium undergoes sp hybridization. So this is one sp hybridorbital, this is another sp hybridorbital, and this will get overlapped with the pz orbital of two fluorine atoms that forms there is along the internuclear axis that forms two covalent bonds between two fluorine atoms. All right. Now, so the average angle between the two adjacent covalent bonds in a covalent molecule is called bond angle, right? So this can define this is the average angle between two adjacent covalent bonds in a covalent molecule is called bond angle. Bond angle of different covalent molecules is similar? No, this is different for different covalent molecules. Then how can you know is this is decided by certain factors. Now we are going to discuss factors influencing the bond angle. One by one. First one, bond angle is directly proportional to electronegativity of central atom. It is directly proportional to electronegativity of central atom. Okay. For example, if you take ammonia NH3 and the phosphine PH3 and the phosphine ASH3 and the active that is SPH3 styrene, right? So these are all hybrids of 15 group elements. If you ask bond on the order base, so nitrogen is more electronegative. You have more bond angle. Next phosphorus is next arsenic, next antimony. Here nitrogen NH3 having 107 degrees, so it undergoes all these atoms all having no electrons, and all these undergoes sp3 hybridization. sp3 means the tetrahedral bond angle that is 109 degrees 28 minutes, but because of low pair of electrons, it causes repulsions under the bond pairs. Because of that, the tetrahedral bond angle 109 degrees 28 minutes, it changes to, it reduces to, decreases to 107 degrees 28 minutes for nitrogen. This is for 92 degrees for phosphate. This is for 91 degrees for oxide. This is for 87 degrees. Like that, the bond angle is progressively decreases. Why? Because as electronegativity is more, the bond angle is more. That too, size is less. Next. The same manner, one more example for that same factor. Another example, H2O, this previous examination question, H2S, H2SE, H2TE. So what the increasing order or maybe order of bond angle of these hydrates of 16 group elements. So no doubt in all these two molecules of electrons are present, but oxygen electron activity is more. That's why we have more bond angle. Right. Next, second factor, bond angle. Bond angle is inversely proportional to number of lone pairs of electrons. This inversely proportional to number of lone pairs of electrons. How? There is, I'll give an example. Take methane and then ammonia and then H2O. As you know, in methane, lone pairs of electrons are zero because all four valence electrons are participating in bond formation. But in ammonia on nitrogen, 5 electrons are there. Among that, 3 valence electrons only involved in bond formation. 2 electrons which are called lone pairs, 1 lone pair is present. And in H2O, in the same manner, 2 lone pairs are present. So all these carbon atom and nitrogen atom and oxygen atom, these are the central atoms. The central atom undergoes in all these 3 compounds. The central atom undergoes sp3 hybridization. sp3 means what we expect, tetrahedral geometry. Tetrahedral geometry means bond angle how much? 190 degrees to 20 degrees or no. Here no lone pair. That's why no repulsance. It cannot deviate the regular bond angle. So the molecule having regular bond angle. That means if a molecule do not have any lone pair, there is no repulsance, only bond pairs are there. So that's why the molecule having regular geometry and regular bond angle. Normal bond angle. Normal bond angle, how much there is tetrahedral bond angle? There is 190 degrees to 20 degrees. But in case of NH3, because of one lone pair is there, this lone pair causes repulsance on the bond pair. Because of that, the regular geometry is decreases, and this how much it is 107 degrees to 8 minutes. And here 2 lone pairs are there. Because of that, number of lone pairs increases, bond angle decreases. That's it, over. So the simple trick you have to find out is as number of lone pairs increases, bond angle decreases. Why? Because lone pairs are batchless, they are not married. So that's why between the lone pairs and lone pairs, repulsants are more. The 2 lone pairs are there. With the lone pair repulsants are there. The lone pair bond pair also repulsants are there. That's why the strength of repulsance is maximum because of that more deviation of bond angle. That's why in H2O the bond angle is 104 degrees 30 minutes. This is 109, this is 107, this is 104. That means all having a sp3 hybridization, but because of this lone pair, whatever the bond angle is reduced as that means bond angle is influenced by the fact that number of lone pairs. So number of lone pairs are more, repulsance are more because of that bond angle is so much reduced as. Right. Next one. Next, another one, third factor. So bond angle, okay. So for example, if the molecule are having, if the covalent molecule having same hybridization is same, then number of lone pairs are also same. And it undergoes same hybridization. Then how can we say bond angle? That is, next factor is the molecule, the 2 covalent molecules or 3 covalent molecules, all the molecules are the central atom undergoes same hybridization and number of lone pairs are also same. Then the bond angle is decided by there is central atom and bonded atom. That is electronegativity of central atom and bonded atom. What is CA? Central atom. And what is A? Bonded atom or side atom. Right. So this is the that means here I'll give for your convenience under two subheadings. One is first one is so 3A. What is that? The bond angle is inversely proportional to electronegativity of central atom. Inversely proportional to electronegativity of central atom. Right? How that is here. For example, if you take it here, HF is there, HF. Okay, and if you take it here, NH3 is there, NH3 is there, right? NH3 is there, and then you take it here, H2O is there, H2O, right? So here, electronegativity of what? Central atom, okay. Here this is the central atom, hydrogen, here nitrogen, and here oxygen, right? So this already here I give the list for H2 and H3. Okay. So then I'll make here one more thing to remember, that is to take it to CH4, right? CH4. In CH4, the bond angle is tetrahedral, and here it is not a tetrahedral. It is decreases, and here it is a high. What happened? Number of molecules are more and more increases. So that's what happened here. This is a linear geometry. And the electron density is more here, and this is here the geometry is pyramidal geometry, and here this is tetrahedral geometry, no lone pair. That's why the bond angle is how much? 109 degrees 28 minutes, and the bond angle is how much? 107 degrees 28 minutes in ammonia, and 107 degrees 28 minutes. 107 degrees 28 minutes, and here the bond angle is linear geometry. So, but here three lone pairs are there. As you know, the fluorine having total how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. So three lone pairs are there. That's why repulsions are there. That's why linear geometry. Linear means 180 degrees. So it is reduces. It is less than 180 degrees. Less than 100 degrees, it is approximately here, it is 150 degrees. So that's why what happened is 150, is 107, is 109. Why? Because here electronegativity of central atom. Electronegativity of central atom. Here central atom is what? Fluorine. So 150. Here central atom is what? Nitrogen. 107. Here central atom is what? Carbon. 109. That means here, so it is depends on electronegativity. No, but here one of the thing is, the main thing is here number of lone pairs. Here lone pairs. Here one lone pair. Here two lone pairs. So this is a combined effect of electronegativity and also number of lone pairs. Okay. All right. So this is it is a combined effect of electronegativity and also number of lone pairs of electrons. These two combined effect will decide the bond angle of these molecules. Right. Next one. Another one is bonded atom or side atom. And for this, one more example I'll give you for this central atom. Here NCl3 and here 3Cl3. So both have number of lone pairs are same. Nitrogen and phosphorus both undergoes same. Both undergoes sp3 hybridization, and both having one lone pair of electrons. So then, which one having highest bond angle is this decided by central atom here. So the central atom, nitrogen, here central atom is phosphorus. The electronegativity of central atom is more, so that's why bond angle is more, right? But here electron is less, bond angle is less. So that's why here this is not inversely proportional. This is directly proportional to electronegativity of central atom. This is directly proportional. Here also fluoride is high electronegativity, high bond angle is the right. 150 right. 150 right. Got it. And here this is what? So this is this is the lone pair of electrons. Lone pair of electrons. Got it? Okay. Here how many lone pairs are there here? No lone pair. And here one lone pair. So lone pairs are there. What happened? Decreases. 109, 107. Then here these two. What about these two? Here central atom more electronegativity, and this is less electronegativity. That's why it is more. It is less. Got it? Yeah. Please. And here also NCl3, PCl3. So both undergoes same hybridization and the same number of lone pairs of electrons, but it is decided by this directly proportional to electronegativity of central atom. Next, another one is bond angle is inversely proportional to electronegativity of bonded atom. Ba means this is, or you can say side atom. Bonded atom or side atom. Atom which is make a bond with the central atom is called bonded atom or side atom. Right. Now, for example, here, take it here HF and okay. Side atom, how to make it different side. Okay. Yeah. So PF3, PCl3, PBr3, PI3. Here, what is the central atom? Phosphorus. Central atom, phosphorus. Okay, all have the same central atom. So, what is the bonded atom? Here, fluorine, here, chlorine, here, bromine, here, iodine. Right. Now, so of this, what is the factor I gave? Electron negativity of the bonded atom is more. Bond angle is less. Bond angle is less. Right. So here, fluorine electronegativity is very high, but here iodine electronegativity is very less. That's why. So electron is less means bond angle is more. Got it? Like that. Understand? Next, one more example. Take it here NCl3. NCl3, right? Yeah. This. Okay. We'll take it here. NCl3 and NBr3, NI3. That is different. This is different. Here, central atom is nitrogen, but with the bonded atom here, chlorine, bromine, iodine. Right? Now, so what is the rule here? That is the factor. If bonded atom electronegativity is more, or left angle is less. So here, this less electronegative, this more bond angle, this more electronegative, less bond angle. Right? So these are the factors which are influenced by bond angle. Right? Next one. So this is about the concept of bond parameters. Next now. A covalent bond is formed by equal contribution and equal sharing of electron pairs. Right. Then it is of two types we did. There is single covalent bond, last class, a double covalent bond, triple covalent bond. It is also based on polarity. It is of non-polar covalent bond, polar covalent bond we did, right? Next now, what are the properties of covalent molecules? So ionic compounds properties we did, right? The same manner, what are the properties? Properties of covalent molecules or covalent compounds. Once you know ionic compounds properties, just everything is mostly opposite. You can compare it also. See. First one, physical state. Ionic compounds are existed only in solid state, but covalent compounds are existed. Some are in gas state, some are in liquid state, some are in solid state. Also, mostly majority gas state. Yeah. Next one, density. Ionic compounds have high density, more density, but covalent compounds are less density. These are soft. Ionic compounds are very hard, but covalent molecules are soft. But exceptions are there here. Majority of covalent molecules are soft. So major majority are soft molecules, but some exceptions are there. That is, some of the covalent molecules like diamond, graphite, silica, silicon carbide, these are all having high density and they are very hard. Or dust, you can say, dust. Why? Because they form three-dimensional network-like structure. So all the atoms are close compact arranged in all the directions. So that's why that forms a network-like structure. Hence, diamond, graphite, silica, then silicon dioxide, silicon carbide. These are all very high density and very hard. Next, melting point and boiling point. No, ionic compounds have high density, so very hard. So that's why they have high melting and boiling points. But here, covalent compounds are majority are soft. That's why they have low melting point and boiling point. But in case of these covalent molecules, because they are very hard, they have very high melting and boiling point. But general sense, most of the covalent molecules have low melting and boiling points. Because here the molecules are formed, but their ions are there. With the two ions, opposite ions, strong electrostatic attractive forces are there. The two ions are strongly held together because of strong electrostatic attractive forces. To overcome that forces, we have to supply high temperature to come from one to other, one physical state to other physical state. But in case of these covalent molecules, covalent bonds are there. Covalent bonds are very weak bonds compared to electrostatic ionic bonds. So that's why we need to supply. That will be very softer. That's why we supply low temperature to convert from one physical state to other physical state. Right. Next one. Conductors. So generally, ionic compounds are good conductors of electricity because their ions are available. The free ions are there. Due to mobility of ions, they can act as good conductors. But here, covalent molecules are bad conductors of electricity, or you can call as insulators. Because why? The reason is in covalent substances are treated as molecules. Molecules don't carry electric current from one to other place. So electric current is carried by flow of mobility of electrons or mobility of ions, but atoms and molecules do not carry. These are also what are there. This is except for graphite. Only one exception is there. That is called graphite. Graphite is a good conductor of electricity. Why? Because in each graphite, in the graphite on each carbon atom, one free electron is there, that is mobile electrons. So carbon having 4 valence electrons. Among the 4 valence electrons, it uses 3 valence electrons to have 3 covalent bonds with 3 carbon atoms. And still on each carbon atom, one free electron is present. There is a mobile electron which can carry electric current from one to other place. That's why graphite is good conductor. But except that, remaining all covalent molecules are bad conductors of electricity. Even though diamond, silicon, even though they are hard also, but conductance is bad or bad conductors. Why? Because here molecules are, so the covalent substances are as molecules. Molecules do not carry electric current. Next one. Chemical reactions. Chemical reactions between the two covalent molecules is very slow. Why? Because in covalent molecules, two covalent molecules want to participate in a chemical reaction. But in this covalent molecule, the second atom bonded atom, covalent bond is present to break the covalent bond. They can also not break the covalent bond. To break the covalent bond, and then this molecule they are combined together to get a new product. So to form a new product, you have to make a new covalent bond. That means one covalent bond is break up, and new covalent bond is back up. So there is break up and back up is some time. So that's why it takes some time. That's why this the reactions between the two covalent molecules in the reaction is slow. Next one. Solubility. Right. Generally, ionic compounds are solubly polar solvents. The dogma is that like dissolves like. That means any compounds have ions are there, positive, negative charges are there, and there is solubly polar solvents. There are also bipolars are there. But covalent molecules, the covalent substances are exist as molecules. Molecules do not carry a charge. The whole molecule is electrically neutral. That's why. So covalent molecules are soluble in non-polar solvents. Non-polar solvents like there is organic solvents like carbon tetrachloride, carbon disulfide, benzene, ether, like that. These are soluble in non-polar solvents because they are non-polar. They are also soluble in non-polar solvents. Except so a few exceptions are there. That is which alcohol. Alcohol is an organic compound. It's a molecule only, a covalent molecule only, but it's soluble in water because it forms hydrogen bonds with water molecule. Because of that, it's soluble in water. And if you take a carbohydrates, there is a sugar, sucrose, or glucose, starch. These are also organic molecules only. These are covalent molecules, but there, if you dissolve water, this slowly cyclically dissolve in water because there are also forms hydrogen bonds with water molecule. Except few exceptions. In general science, these are soluble in non-polar solvents. Next one, isomerism. Isomerism. So covalent compounds are directional property. That is, the covalent bond is formed by overlapping of atomic orbitals of the two atoms. So, on which direction they get overlapping, that will decide the arrangement of atoms around the central atom, that will give particular geometrical shape. That is, the covalent molecules, the atomic orbitals are overlapped in such a way to give particular geometrical shape of the molecule. So that's why there are particular directional properties there. So they are arranged maybe a linear or a trigonal or a tetrahedral. So that means that is they have directional property. That's why they exhibit. So covalent molecules are having directional property. That's why they exhibit isomerism. That means the same molecule can exist in having same molecular formula but different structural formula because of arrangement of atoms is different. Because of that, structural formula will be different. So such property is exhibited with the covalent molecules, that is called isomerism, because that isomerism property is related to directional property, how they are bonding and how they are overlapping, and which direction they are overlapping, and how they are arranging, and which geometrical shape they are arranging, that will decides the isomerism. So that's why covalent molecules exhibits isomerism because they have directional property. The bonds are a directional property, right? Yeah. So now, so this is about the properties of covalent molecules is completed. So yeah, next time is over. So that's what today the session is ends up. Next class we'll start the session with new concept, that is theories of covalent bond. That is so okay. Till now we discussed about how covalent bond is formed. That is how different types of covalent bond. Then to explain the geometrical shape of the covalent molecules, different theories are proposed by different scientists. There is called valence bond theory, and then Westphal theory, and then aberration concept, and then molecular theory. It's all discussed further. It's not very important. So okay, so now session is yes, sir. Next class will be 5 minutes. This is